Hello everybody, welcome to another ME296 lecture, this time electric motors. We're going to discuss a little bit about the construction and then a little bit about their limitations. So first of all, motors are a kind of transducer, and a transducer converts energy from one form to another. This can be from heat energy to electric energy in like a geothermal plant, or it can be from chemical energy to mechanical energy like a battery to a motor or anything like that. Anything that converts energy from one form to another form is a transducer. There are three broad types. The first one is called a sensor. And a sensor receives and responds to a stimulus, and it responds in the form of a signal which contains information about the stimulus. And we've used this in one of our labs in this class, and it was the thermistor. It received a stimulus in the form of heat, and it responded by changing its resistance, which contained information about the temperature that it was measuring. And then we could use that to do other stuff with the rest of our circuit. The second kind is called an actuator, which converts energy into kinetic energy specifically. And these are important because they allow control systems to physically interact with the environment. If we had a control system that would, say, like shut off the flow of water if it detected that they were flooding something, then you would need an actuator to physically close the valve to turn off the water. And the last kind is a bidirectional transducer. These can receive or produce energy. The most common one of these is an antenna. Think of like a walkie-talkie. It's only got one antenna on there, but you can listen to other people talk because it's going to receive the energy from their walkie-talkie. And then when you want to talk, the antenna sends out a signal based on what you said. So it can send and receive energy. All right, now on to motors specifically. And we're going to talk a little bit about vocabulary first, because it's important to get all our words straight so we don't have to keep referring to the same thing in different ways. So the first thing is the rotor, and this is the part that moves. It doesn't always rotate, but in general, in this class at least, when we talk about rotors or motors, we're going to talk about rotational motion, so a rod that spins along its axis. Then there's also the stator, and this is the part that does not move. And it's important to distinguish this from like something, say the housing, which has no part in producing the motion. The housing doesn't move, but it doesn't help the actuator rotate anything either. The stator does. And in our case, it's constructed of magnets, or it can also be like a wire or a wire coil to generate a magnetic field. But the important part, stator does not move, but does help produce the rotational energy. Third thing is the bearings, and these support the rotor and they allow it to move more freely. Think of rolling your hand on a marble on top of a table. That marble is acting as a bearing because it is giving you more freedom of movement with your hand. You can move more freely. If you take the marble away and put your hand flat on the table and try to move it around, it's harder to do. So the importance of a bearing is that it reduces the friction between the parts that don't move and the parts that do want to move. Then there's also the air gap, which is specifically most important for us because we're dealing with electric motors. And the air gap is the distance between the rotor and the stator. More on that in a bit. Then in some motors, there are these things called windings and some things called commutators. And windings are generally just wire coils that are used to create magnetic fields, just like an inductor does, but with a different purpose than what normally we would use an inductor for. And then a commutator switches the direction of current in some motors because some motors are designed around having current flow switching back and forth. So a commutator allows that to happen. I'm not going to go into how, but you can look up just commutator and there's a couple of basic designs that should illustrate it. It's not a super complicated concept, but it's not really relevant to this class. Now for how does it work? Motors are a transducer, and they convert energy from one form to another. The energy in a circuit is in the form of voltage, which is a difference in energy specifically, a difference in energy. And we use that energy to make electrons move and produce a current. So we're causing something physical to move with our electric field or our voltage field. And that's called the electromotive force, because we're forcing something to move. We're applying force to something. And it's the same force that allows a motor to work. It's rotational instead of in a line like current, but it's the same thing. And we do that with magnets and coils. And to generate that magnetic field, we use this equation, which tells us the magnetic field of a moving electrically charged particle. And basically what it says is B is the magnetic field is equal to the constant out in front, which has to do with how easy it is to transmit magnetic field information from one part of our system to another part, the permittivity, times this fraction. This fraction is the important part. Q is the charge of the particle we're looking at. So if it's an electron, it's 1 electron volt, or 1 fundamental charge value, times the velocity, big V. So faster velocity, it's on top, means greater magnetic field, lower velocity, smaller magnetic field. And then it's cross product with that r hat. And r hat is a normal vector that has to do with the direction, the vector that we're looking at from where we're measuring at to where the particle is. And then that's over r squared, because everything falls off as 1 over r squared in mechanics and electromechanics. But the important part for this equation is you have a higher velocity, you have a greater magnetic field, and it falls off as 1 over r squared. What does that look like? It looks like this. If the green arrow is the motion of our electrons, then we have a generated magnetic field that heads out normal to the direction of motion. Now this isn't strictly physics, but it's good enough for this lecture. So the magnetic field, the blue one, is one side, positive or negative magnetic field, and then the red one is going to be the opposite. So blue is positive, red is negative. And you have to have both because there's no such thing as the magnetic monopole. Positive and negative together always. And that's going to be important when we look at exactly how this generated magnetic field makes movement happen. So how does it do that? First, let's set up our motor. We have a rotor in the center in silver, and then in it we have a current. So let's say we have like a rod, and then we've laid wire through it so that there is a U-shape bend right there, so that if you are on the left side of the rotor, as we're looking at it now, current is flowing up, and on the right side it's flowing down. Then on the outside we have these two magnets, and these are going to comprise the stator. And there's different ways to do this. We could have the magnet on the rotor and the current on the stator, or any kind of thing. But the important part is the interaction between the fields and the current. The broad strokes way that motors works stays the same no matter the configuration. There are little implementation details that kind of change things, more efficient, less efficient, what have you, but they all work generally the same. So here's our setup. Rotor with a current in it that, depending on what side of the rotor you're on, it's moving in opposite directions. And then you have the stator, which has a north magnet and a south magnet on either side, on opposite sides. So let's start with our current. Flowing up, let's say we have our blue side of our generated magnetic field interacting with the north magnet. and the red side interacting with the south magnet because they're on opposite sides of our current flow direction. That's going to be, just for the sake of this slide, a repulsion between the two blue ones and an attraction between the two red ones, because like repels like in magnetism. So you've got this repulsion between the north magnet and the wire that's on that side, and that wire is also attracted to the south magnet. So what's going to want to happen? It's going to want to move away from that north magnet toward the south magnet. So we're flipping direction. It's going to want to go there. And you may be thinking to yourself, that's great, we got it to flip over one time, but we want it to continuously move. And we do that with the commutator. We're just going to leave it a black box for now, but the commutator is going to do something, and it's going to flip the direction of the current. So now we have a repulsion between the north magnet and that particular wire, and an attraction on the other magnet. So it's going to flip again, and it's going to keep doing this over and over again. Flip, flip, flip. And the commutator is going to change the direction of the current based on the orientation of the rotor. So this is going to produce a smooth, somewhat smooth rotation. If there's only two magnets, you're going to have periods where the repulsion and attraction effects are stronger or weaker, and that's going to produce fluctuations in the amount of torque we're applying, or the rotation speed that we're getting out of our motor. And you can add more magnets to smooth this out, and that's one of the things that people measure when they're looking at electric motors. And this is very similar to the ripple current we were looking at for our full bridge rectifier, where we want continuous steady value, but we get some fluctuation just based on how physics works. So let's talk about some limitations. We live in the real world, and there's no such thing as 100% efficiency. We're not going to be able to convert 100% of the voltage that we apply to our motor into rotational kinetic energy. And different designs are more or less efficient than other designs, more or less suited than other designs for specific tasks. But there are common methods of energy loss that all motors have. And the first one is friction, mechanical interaction between components. So if our ball bearings aren't very good, we're going to lose energy in that rotation. And if we have a very good set of ball bearings and we grease them up, we're going to have much better rotation, much less energy lost by friction. There's other things that can do that too. Maybe the commutator is designed in such a way that we lose energy when the commutator works, that kind of thing. Then there's the air gap. Remember that fields fall off as 1 over r squared. So we have a loss in field energy as we move away. So if we have a large air gap, that magnetic field that the stator has, and that is produced by the rotor wires, is going to be smaller if we have a large air gap. But if they're very, very close together, it's a much stronger electric field. But if they're too close together, maybe they're touching, then we introduce additional friction to our system. There's also heat generation. Every joule that leaves our motor in the form of heat is a joule that's not being used to turn that rotor. And you can't really avoid it. There's real resistance in everything, in wires. No room temperature superconductors in our parts. So we're losing energy in the form of heat. Then there's also noise. Vibrating something takes energy, and vibrations make noise. So if you can hear the motor, that's energy being lost to the system. It's like a Harley Davidson. They make all that noise, and all that noise is just energy not going to make them go faster. And then there's also field interference. Electromagnetic fields don't stop where we want them to, for the most part. We can build a Faraday cage and everything, but that's usually pretty expensive for parts that it's not super important to do. But if we have other components around our motor that generate electromagnetic fields, this might interfere with what's happening inside the motor. Or maybe our motor is designed poorly and the interactions reach too far and all the way across the motor to interfere with what's supposed to be happening on the other side of the motor. And this is going to introduce loss or unwanted behavior, which is just as bad as losing energy, because we want everything to be nice and predictable in motors. Think of an electric car, of a Tesla. We don't want a Tesla to have unpredictable behavior. That'd be very, very bad for everyone. So we want to minimize field interference. Another thing that can happen is called feedback. And because momentum is a thing, the continuing rotation of the motor can create feedback even if the motor has been turned off by us. For the most part, we cannot instantaneously stop the rotor from spinning. So if the rotor continues to spin, that equation of generating that magnetic field works both ways. If there's a magnetic field, then we have some kind of charge movement. So if our rotor continues to spin, even though we've turned off our motor, that movement is producing energy, and that energy goes back into the wires, and that can feed back into whatever system our motor is hooked up into. And this can damage the circuit. For the most part, with what we play around with in this class, you're probably going to be fine because we're using like a 9-volt battery, and even if you do manage to damage it, you just get another one. They cost, what, $0.25? And the delicate things would be for more practical applications, like maybe you have an ammeter hooked up that only goes one way, or you have a very specific generator that's providing the energy that's very delicate but provides exactly the right amount of energy you need. So it's important to take feedback into account when we're designing motors systems. So that equation again, if B is equal to 0, our velocity is equal to 0, right? Because we cannot change the charge on an electron. The permittivity stuff is a constant in front, and the radius is the distance. That's it. So if we have movement, we have a magnetic field, and if we have a magnetic field, we have movement. So here's a simple setup to illustrate how we can protect against feedback. So let's say we have this one, where our positive voltage generator terminal goes through some kind of internal resistance into the motor does its thing, and then goes back to the power generator. Well and good, until we turn it off, and then the motor continues to spin for a little bit, and that little bit of spin, the velocity that we have, is producing a magnetic field. The magnetic field is causing the electrons to continue moving even more. So it's a little bit of a feedback thing that bleeds off over time. And that magnetic field causes the electrons to keep moving some more, and then that's providing a current, and then that current is feeding into our voltage generator even though it's off. And we don't want that to happen. Well, we can just put some diodes in there to prevent it. We can make sure that the positive side only goes out and the negative side only goes in to our voltage generator. This is going to protect our voltage generator from unwanted feedback from our motor. Okay? So the next lecture we're going to do is a lecture on a couple of examples of control systems and how they're implemented. And I think that that should do it for this one. All right. Thanks for watching.